This video provides an overview of different magnification approaches for gaze-based interaction. The demo is implemented in the multi-modal interaction concept for efficient input, or short, M²ice. In M²ice, a video-based eye tracker mounted below the screen is used to record the movement of the gaze point. This often suffers from inaccuracy, which is caused by the underlying hardware and its limitations like resolution, and physiological limitations like microsaccades. This often causes the detection to be off. This means that the reported gaze point is not quite matching with the real gaze point of the user. This can cause interaction issues and ultimately leads to frustration, as the software can't be reliably used. To overcome this, M²ice, like many other gaze-based interaction systems, provides a magnifier to enlarge elements, which makes it easier to hit them in interaction. There are different types of magnification that can be used in gaze-based interaction. Those can be broadly divided into three different categories. Linear magnifiers are very familiar and apply the magnification evenly throughout the enlarged area. Nonlinear magnifiers mostly come in the form of fisheyes, which use a different kind of transformation where the enlargement is not quite equal throughout the area but stronger in the center. Hybrid linear fisheye magnifiers combine both and have a linear center and a fisheye distorted edge. All of these categories have their own advantages and disadvantages that need to be addressed when using them. While the linear magnification is distortion-free and thus preserves the relative size and form of objects, it loses the structural context of the surrounding information, as some information is occluded behind the opened magnifier. Nonlinear magnification uses a distortion to preserve the structural context of the information by not occluding parts of the screen, but rather seamlessly integrate into it. But inaccuracy can be a problem when the focus is slightly off-center of the opened magnification. The hybrid approach compensates for this, as the focus relocation due to inaccuracy is only happening inside of the linearly magnified part, while still preserving the structural context through the outer nonlinear area of the magnification. One problem that remains with the use of the hybrid linear fisheye magnifier is what to do on the edges of the screen. Shown in this image, opening a magnifier near the edges of the screen would lead to information being pushed outside of the visible screen area. This can be overcome with either a shrinked workspace that has room for the magnification, but that is highly impractical as it limits the usable screen area in every situation, even if no magnification is used at all. Another way to fix this is to relocate the focus to a point where no information is pushed outside of the visible area. While this can work in some cases, it limits the usable size of the magnifier. In the most extreme case, on the edges of the screen, only a quarter of the magnifier is visible, limiting its effectiveness in interaction tasks. So the question remains: how to magnify on the screen's edges without disturbing the user? One possible answer to this can be the use of the dynamic teardrop magnification. The dynamic teardrop magnification extends the normal hybrid linear fisheye with the special solution just for the borders and corners of the screen. To enable this, the screen is effectively divided into three different kinds of areas, with each opening up a different kind of magnifier if requested in that region. The first yellow area opens up the normal hybrid linear fisheye magnification, as it is safe to use in this area without any loss of information. If the user opens up a magnifier in one of the blue areas, a special border magnifier is applied that is looking, like its name suggests, like a teardrop that is falling into the screen center. The corners, which are marked green here, have a third magnifier type applied that provides a similar teardrop solution but with a few enhancements for the corner cases. This means that the complete teardrop magnification solution consists of these three categories of magnifiers, with each of them serving a special purpose. Now let's have a look at what this magnification looks like in a short demo. As you can see here, a click in the center opens up the normal hybrid linear fisheye magnifier. It can even reach inside of the outer areas of the screen as long as no information is lost. A click near the edges of the screen opens up the border version of the dynamic teardrop magnification with an animation that provides visual guidance for the focus relocation. Its size is dynamically adjusted based on the gaze position while opening up the magnifier. Last but not least, the corner version of the dynamic teardrop magnifier works in the same way, while using a specialized shape for the corners of the screen. The combination of the hybrid linear fisheye magnifier with the teardrop magnification preserves the structural context and features a dynamic size that adjusts to the user's needs. It also works in all areas and solves the problems especially on the edges of the screen. Thanks for watching.